All right. So we're up and running. So everybody sees this, right? Raise your hand if you have problems. Somebody can help you. OK, good. So let's do the cat, dog, mouse example for Lynette. As you know, deep learning and image recognition go hand in hand, right? It's kind of the first good use case that showed that it was a good method. So you see how easy it is. You just have a bunch of imports there. You import H2O, you import pandas, whatever you want to do your scikit-learn kind of environment. And the estimator is now a deep water estimator and that we import. We'll use it in a little bit. So let's execute this cell with Control-Enter. You'll see the cluster has been up for a while. Yours might have been up even longer because we launched these Amazon instances earlier this day. So we basically launched 100 of them. They're 70 cents an hour, so hopefully it doesn't ruin us. You see, it's 8 cores, right? These are not very good boxes. These 8 cores are virtual cores, so it's not really a physical dedicated instance. It's more like a shared environment, so it might be slow at times, but it's good enough to have basic capabilities. So we'll import a cat, dog, mouse frame. That frame is a 2-column CSV file. It's just a few kilobytes, and it has a URL to an image and a label. So the first few are all cats, the next ones are dogs, and then the last ones are mice. And that's only 267 or so images. So it's a very small data set. The point is just to show you that it works and that you can iterate quickly. And with this definition of a frame that we need for image recognition, it's very versatile, right? This path can go anywhere. It could be Hadoop. It could be a URL to some website that also works. You can just provide images as pointers. So you don't have to actually ingest any JPEGs into H2O in memory and store them or anything. This could be a list of 1 million URLs. It will fit in a few megabytes, but actually the images themselves could be a few terabytes if they're all like high-resolution images. So this is the way we do it. We can look at the first few images. We sample a bunch of images. In this case, we look at the first, just 10 random samples. And you see there's a mouse, another mouse, cat.
Are these images on the...
These images are on the EC2 instance, yes. So we uploaded a bunch of files. So this model will now learn to recognize these animals, right? But obviously with 300 images, what you're going to do is you're going to overfit on those. And then if you want to generalize, the answer will be it's not very good because all it did is recognize this white thing was a mouse or something. If it's white, then it's a mouse. But if it's white somewhere else, then maybe it's a cat because there was a wall there that was also white in the background. And it just memorized that. It didn't actually learn what a cat is. If you want to learn what a cat is, you need more images. You need tens of thousands of images for a cat and tens of thousands of images for a dog and so on. So big data is important. What's going on? There's something else. Oh, it's just a password manager. So yes, I'll make it this one a little bigger. How do I get rid of this? Here, with this. So let's go back to the cat, dog, mouse. So this is the Lynette architecture. You saw it earlier. Fabrizio showed the code for it. It's basically a bunch of convolutions. If you don't know what that is, Google it later. It finds out basically what an eye does, the Fourier transforms that I mentioned earlier. It does the physics of the vision task. And here with this NVIDIA SMI command, you can actually check out what hardware you have for the GPU. And it will tell you this is a K520 with 4 gigabytes of RAM, and it's not busy right now at all, even though a Java process is connected to it. So this Java process is us saying, be alive, but we haven't yet started training. And now here we actually train. So Control-Enter, and now it's training. And the beauty of H2O is that you could now go to Flow, the other IP address, and you can look at the water meter, and you'll see that actually there's something going on in that cluster. There's some CPUs being used to process those images. But it's not a lot of work because it's a small data set, so you won't see that to be that busy. So by now it's done. It shows you the output because we did a model.show at the end. Basically tells you it's a 1.6 megabyte model. So the model itself is rather small. It's only 400,000 float single precision numbers, right? And those 400,000 numbers are basically the model. If you learn them well, you know how to make this model. And we trained on 134,000 samples, but of course they were sampled from the same 300 or 200 images. So over and over again, we just did 500 iterations over the data set. And that's called a epoch. So we did 500 epochs. And you see the actual image size is such that we have 2,352 input neurons into the neural net. And the error is 0. We got it all right. Does everybody else have a 0 there, or did somebody have a model that didn't quite converge perfectly? You had one that had an error?
007.
Okay, you got a small error. So not everything is the same every time you run it because we didn't set a seed. And also GPU codes are notoriously irreproducible at times. It depends on what the state is on the GPU. You have to do everything right to seed everything all the way down. And sometimes the latest version or so has an issue with the random generator or so. So CUDA 8 is required to run on a Pascal GPU, the latest GPUs. If you use CUDA 7.5, it's actually not going to work because the random generator was screwed up. So you have to be careful sometimes with the randomness. But it basically worked. It learned it. You see, it took 23 seconds to do 500 epochs. And the error went down to 0 even earlier. Now you say you want to build your own graph. You just define one like here. This is using the MxNet library, which we also ship as part of the distribution of H2O, of deep water. It's basically one jar file. Just like you download H2O, you download this one. That's a little bigger. It's 400 megabytes instead of 100 megabytes, and it contains MxNet inside, it contains Tensorflow inside, it contains Caffe inside, and it has these libraries inside as well. So right now, actually, this MxNet library is not inside the jar, but it's a separate thing that you have to like command install or install.packages in R or a pip install in Python. It's just another package. But if you have that package that works with our distribution, then you have the same version of MxNet, same version of TensorFlow, and that universe will work. Was there a question?
You just answered
Oh,
it.
that's the answer. Okay, so we basically make sure that the MxNet Python bindings are compliant to our backend that we compile against, right? And the MxNet version we compile against is the latest top of tree as of a week ago or so. So we try to keep up to date with the latest developments in all these dependencies that we have. So you can change something here and see what happens, right? For example, you could change the number of filters to be 50 or so and see if it makes it more accurate. But obviously, it's already sharp enough to just overfit on those 200 images. So this is not the best model to do that. But you see how it works. You basically have a graph that you make with this method here. That's the function here. This graph is something that has a .save method, and that saves itself to a JSON file. You can actually look at that JSON file and see it's just text, just similar to what Fabrizio showed earlier. It defines each layer, says how big it is and all that. And you can also plot it. So when you plot it, it actually shows you the graph in graphical form. And you see it's a linear model, basically, one pipeline of operators in a row. Right? One input turns into something else, and so way up. It doesn't have to be a string. It could be like parallel threads going up that are connected at different places. And we'll show you such a graph later. But if you run this here, it's going to be the same model as the other one, just this time you actually specifically build a LeNet model. And if you don't know how to build that, you just Google it, LeNet MxNet or LeNet TensorFlow or LeNet Caffe, and you'll find the definition, right? Now, this was using the GPU. You saw it was 20 seconds or so. Now, if you set GPU equals false, it's going to be, oops, it scrolled up. So this took 22 seconds. If you do GPU equals false, it's going to be slower. However, we only trained for 10 epochs instead of 500, and it roughly takes the same time. But we actually did only 1/50th of the work. That's why I said it's about 50 or 100 times slower on a CPU. And that's not the most optimal CPU implementation. It's using one thread, it's using BLAS, it's not MKL, it's not a Xeon Phi, it's not hardware optimized, it's just a off-the-shelf standard library. Obviously, you could do better than that, but you cannot beat a modern GPU that easily. You would have to have custom ASIC to do that. So does anybody have problems with this script or questions? Otherwise, we can move on. So let's click here on File and say Close and Halt. That just gets rid of this. And you're back to this Jupyter Notebook front page. So let's do the same thing now from Flow. You go to the 54321 port. You can see at the very top. If it's too small, I'll make it a little bigger. Now for data, you'll say import. And under search, you'll type big data / laptop / deep water, I think. Yep, deep water, ImageNet, cat dog mouse CSV, and you press enter. Once you get used to this interface, it's actually very good. It's just sometimes it feels a little awkward with the tabs completion and all that, but we can actually import a whole folder of files all together. It's not just one thing. So you have this. This is kind of a very powerful API. Once it's at the bottom, this file, you click import. Did you get to that point? So big data, laptop, deep water, ImageNet, cat, dog, mouse. That's that same data set. You import. You click parse this file. You have to click a few times. This basically does a preview of the file and says, it looks like a CSV. It looks like it's space separated. It looks like the first row already has data. OK, the first column is a string, which is the path. Yep. The second column is an enum, which it is. It's a category. Looks good to me. I say parse. And it's super tiny. You just parse that file. We can look at that file. You see the same column types, obviously. Yep. I can click on View Data. And I see all that content. If this went too fast, doesn't matter. As long as you get to this frame that's somehow parsed, get to this point here. If you have questions, people can help, or your neighbor has figured it out. You basically have to parse this frame. Now you're in H2O. This is actually a frame that's distributed on this one node cluster, if you want. It's 17 kilobytes, has 267 rows. It has one little chunk. So it's not really parallelizable yet because it's so small. But it doesn't have to be because the work gets done on the GPU anyway, not on the CPUs. So if you're at this point, you can now click on Build Model, because you want to build a model on this frame, right? And you actually notice that the frame was called cat_dog_mouse_1 or something, because we already had one in there from your Python script that we just ran. So that's why it appended the name. So let's click on Build Model. And then on the models, we can do anything we want here, gradient boosting, for example, but that wouldn't be that good with those raw pixels, although it might actually overfit and memorize it too. However, a random forest or a gradient boosting machine is not meant to learn from these strings, because we give it a string. The path, can't do anything with it. So it's not going to work. It will say, sorry, there's not enough columns to work on because it's a string column and I have to ignore it. Only deep learning or deep water here knows what to do with a string column. So we say deep water. Deep water is just deep learning, but it's the GPU version of deep learning. We didn't want to rewrite the old code to do both things and make it all confusing. This is just another name for something fresh. And some of the capabilities are duplicated because you can run deep water or deep learning, the CPU implementation. You can run the old code or the new code on like a regular data set, right? But you can compare the two. It's actually an interesting exercise which we can do just in a few minutes. So you run deep water on this cat dog mouse. You'll see that there's another one there as well. You can use the old one or the new one. Who cares? It's the same thing. We don't have a validation frame. The response column is column 2. And then you can scroll down and change the network to be LeNet. And activation, you can't set that right now because it's only for a user-defined function where you don't need these, right? The user-defined function, LeNet, for example, that you specify has the activation in it. So there's no point in saying I want LeNet and I want to set it to rectifier because it conflicts. What does it mean, a rectifier for a whole graph? This activation is only used for like a fully connected neural net, the old school way, just like H2O deep learning. So if you specify your hidden layers here like 200, 200, then you would have to say what activation function it is. So we're trying to make it easy for the standard old school fully connected neural net and for the super complicated graphs that you can provide. But for now, we just pick a preset LeNet and we go all the way down and say go. Everything else is default. And this will just run and train on it. And all it did was 10 epochs because that's the default. Here, somewhere it says epochs 10. And now we can change this here up here. We'll make it, let's make it 1,000 and run it again. So Control Enter. And now it's going to run again. So this is how it works. You can click on View as it's running. And then you can click on Refresh also as while it's running. And now it will show you in real time how it's moving along, right? And this will converge at some point, roughly 500, as we saw earlier. It should just overfit on that data set and be done with it. And this is basically the cool thing about H2O is you get real-time insights into the model. You don't just get a bar that says I'm at 80%, but it will actually tell you how the model looks like. And you see a confusion matrix that's diagonal. And now you can stop the refresh and inspect maybe the scoring history. You get this table. You can look at the training metrics. If you want to know what the RMSE is or the log loss or something, you get other numbers. There is a small inspection of this model. For example, you see the learning rate at this moment after 1,000 epochs. We had some kind of decay in the learning rate. It started with some value and then it decayed over time. That's the default. So if you wonder why this is 0039 and not 005, which was the preset that was set in the actual cell up here, that's why. Because we did have a learning rate and a learning rate annealing. See this? Up here. There was a small annealing. And that says for every observation that you go through, it counts as 1/1,000,000th of a decay. So once you have 1,000,000 observations, you divide by 2. It's like the half time, the half decay is after 1,000,000 observations. Anyway, these are kind of the parameters. So it becomes like a regular H2O model. Does that make sense? Is that all good? So we can go back to the Jupyter notebook and run an MNIST benchmark. That's a benchmark that's in reference to Szilard, our friend in LA, who actually built a little website here to start testing deep learning frameworks. And it's very early. He meant to actually not make it public, but we found it and kind of like immediately showed him that we can do this too. And he is using the same instance here as G2 2x large. And it has the same GPU that we saw earlier, and it takes 56 seconds using the TensorFlow backend. Okay? So 56 seconds to build a model. And what model was that? Well, you have to look at the source code here. It's a model that's defined here. These are the graph components. So it's a convolution, rectifier, max pooling, another convolution, max pooling, dropout, and then 2 hidden layers, and then a softmax with 10 classes, because it's MNIST. MNIST is the handwritten digits data set. So you take these numbers, we use the learning rate of 0.5, and decay, momentum, SGD, everything like that. And we just did the same thing in our MNIST benchmark. So again, we start the infrastructure. This is the same instance that he was using, the one with the K520. We suck in the MNIST data set. And we do the same pre-processing that he was doing. So we divide those digits, those grayscale values per digit by 255, because the number is from 0 to 255. There's 1 byte for each pixel, and it's 28 by 28 pixels, so 784 pixel values. Each number is a number from 0 to 255. And we just divide by 255 to make the number go from 0 to 1. And 0 means it's white. There's no pen going over the paper. And we turn this response into a factor with 10 levels, and that's what n classes now is. We have this graph here, same numbers as what you saw earlier, with dropout and everything. So the MxNet package for MNIST looks like just simple, right? It's just a simple problem, 10 classes here. We pass that argument here to the CNN function in the next line. Yep, here. And we save it out to a file. So in future iterations, we will be able to provide the string directly to the call of the model without having to save it to a file and loading it back. Because technically, you're saving it on your client, on your laptop, but then you're loading it on the server. Well, in your case, you're actually saving it on the server too, because you connect it to a server's Python notebook. But normally, you would run your Jupyter on your laptop, right? Not on the server, unless you're using EC2 all the time. So we have to kind of figure out a way to save this JSON on the server. And the easiest way to do it is to just, wherever you have it, you just upload it to the server, and the server sucks in the JSON.
So you're comparing what you're doing with the deep water?
We haven't run it yet. Yeah, so this is the deep water model.
Right. So the MX one is you're running that as well?
No, we don't run anything. We just make a graph. So the MxNet library we load, and then we say, make me a network that has these layers in it, and write that definition to a string, one long file, basically, that's just a text file.
Okay.
And that text file we save to disk, and then we pass that to our deep water call here. And now we have exactly the same parameters as the benchmark. So a learning rate, some momentum, some mini batch, some image shape. We use the first GPU. In this case, there's only one. We don't standardize the values anymore because we already manually divided by 255. We do not ignore constant columns, even though there are some pixels that are always 0. There's never, ever anybody writing in the left upper corner, for example. But we still keep them in there such that the shape of the image is 28 by 28. So I say go, and this is the benchmark, right? Now we can go look at in Flow here in the water meter. If you don't remember how to get there, you have to go to Flow and then admin and then water meter. I like that because it tells you kind of what's going on. You're seeing all 8 CPUs are busy providing data to the GPU. And you can also do a admin profiler, and that will actually tell you what Java is doing. So Java is calling the image train method of the MxNet backend. This is how you can see what's going on in Java. So this is the stuff we had to implement to make this work, right? But you don't really have to care about that. You just see that this is almost done. But you like to see that there's something going on. OK, done. Now we can plot it, see that it converged. OK, fine. We can look at the model's output. OK, fine. The confusion matrix is pretty good. 3 out of 1,000 are wrong in the training data. So it overfits, but not too badly because the actual validation error is not that bad, as we will see in a second. And it trained it in 50 seconds. Did anybody's GPU do this faster than 50 seconds? 48, anyone? 47? Nobody? 47? Do we have a 46? So this is how we do ensembles, right? We just do everything, and then we pick the best and say, well, it was fair. And I was just kidding. So the scoring history is like the short version of the model's evolution. See, the error on training went down to 0. It took 50 seconds to get there. So TensorFlow took 56 or something according to that other benchmark. So we're doing fine in terms of speed, right? It's fast, even though you could say, oh, Java is not that great. Well, actually, it's not bad because you have multi-threading easily available in comparison to like a pure Python version like Tiano. So you get the parallelism of the pre-processing. So we actually parallelize over the image pre-processing. So the mini batch gets created by all the threads in parallel, and they prepare this one mini batch, while another one is already training on the GPU, and then they swap the two. So there's like a cyclic buffer with prefetching and all that. We can do all that stuff in Java in only a few lines of code. And now let's worry about the test set performance. I think the other benchmark was saying something like what did they say was their accuracy? 0.8, 0.9, I think. Here, 0.8, 0.9, that's roughly like percent, right? It's a super small number. It's only like a handful of images are wrong because the test set is only 10,000 images. So I got a 0.8 as well. Anybody 0.7? Yes? You got a 0.7? 0.7 what? 0.79? Okay. I've seen a 0.71 before, so it's also random, right? You get stochastic gradient descent, can get lucky sometimes. But as you see, there's only 10,000 points. So basically, we're doing a good job. This is the standard model on a standard data set, and it's on a GPU, so not much you can do wrong. But basically, we're doing everything right, which is good to know. So now we can close this file, close and halt. Go back to our Jupyter notebook and maybe run something like a credit card default risk prediction. Why not? It doesn't have to be an image. So in this case, we're actually going to load all the different estimators from H2O that are reasonably good. We actually forgot to use the GLM, the gradient, the generalized linear modeling one. Next time, I promise I'll add that one too. But we just have 4 models, and we have a path here to CC default. That's some directory we made that has a file in it. We'll actually import this file, and it looks like a financial data set. Has a bunch of columns, payment amount, and whether or not they will default on their payment next month, right? That's the response. So will they default or not, given the amount they paid in previous times, whether they're married or not, whether they have an educational balance or whatever limit, whatever it is. I don't know what it means, but you probably are more familiar with this data set than I am. This is an open source data set, 30,000 rows, 25 columns. We're going to turn some of those columns to factors. And we're going to say everything is usable as a predictor except for the response. We don't want to cheat that much. And also the ID, we remove the ID because it's not good to overfit on an ID usually, unless there's some time structure or something that we leave that to the experts. Then we're going to do a train validation test split, 80%, 10-10. It's just for fun, cut it up a little with a random column. So this is a way to do this in a scalable way. Not that this data set is large, but if this data set was 200 gigabytes and you did this to in a 10-node cluster, this would be a scalable approach to do this split, right? Because you just have a random column made, and then you subslice that based on the random column. And now we're going to run a deep water estimator on this data set. And notice we don't do anything. We don't do any one-hot encoding by hand, no anything, no standardization. We just give it those raw numbers, right? These are categoricals. These are numbers that are not between 0 and 1 or -1 and 1. It's just a number. So we get a 72 AUC on the validation set. And how do we know that? Well, we passed the validation frame to the model building process. So what happened here is the model trained on training, but it also validated on the validation 10%. And as it trained, it would measure its performance, and it could, in theory, stop early once the validation error has converged. Okay? So that's built in the H2O deep water by default. If you give a validation set, it will check out how it's doing. Once it's done converging, it stops. There's no point in going too long because I will overfit. So you don't have to do anything. You can just pass a epoch of like 1 million, let's say, and it will just still stop after 254 epochs. In this case, we only did default, which is 10 epochs. So only 10 times over the 30,000, or in this case, 25,000 or 24,000 numbers, rows. So we did 240,000 samples, right? 10 passes, because that's the default. I just said, let's do default parameters for every algo, just to be fast. Just let's see how it does. And because we trained on the training and validated on the validation frame, we have those scores in the end of the model. So when we say model performance on validation, that number is already computed during training. We don't need to recompute anything. That number comes out for free. So this last line there is basically just fetching a number from the model that's stored and done. And now we do the same thing using the CPU version. That's the old Java code that also uses all the CPUs, as you can see. This is not using the GPU, this is using the CPU. So we have a deep learning implementation using the CPUs. That's very efficient and accurate. Let's see how it's doing. 76 AUC. It's actually higher accuracy, even though it didn't use a GPU. How is that possible? Well, it doesn't do a mini batch, for one, which means it is a little sharper. Every single observation immediately makes a backpropagation. It also has adaptive learning rate by default. And those two things led to this number being a little better out of the box. Doesn't mean that the other one couldn't be better over time, because you can train faster on larger data structures and larger networks. So you could have made a bigger network. And in this case, you could have said hidden equals 500, 500, 500. And that would have made a 3-layer neural net with 500 neurons each. And at that point, maybe the GPU will already be faster than a CPU. And if you do 5,000, 5,000, 5,000, 5,000, then GPU will be much faster than a CPU. So for large networks, it's actually much better to use a GPU. But for a network with maybe 50, 50, 50 neurons, the CPU might be faster. So GBM is better than those two, not surprisingly. And random forest, what do you think? Is going to be better or worse than GBM? Yes. All right, so now we have that. We predict on the test set, the last 10%, we get some numbers out. As you can see, there's a label, and then there's a class probability for class 0, class 1. The label is assigned by using the threshold that gives you the best F1 score. You don't have to use this. If you're a data scientist, you say, no, I'd rather have a different threshold. And we give you a whole list of all the thresholds and all the metrics for every threshold if you want to see that. But we have to make a default label for those who want to see a label. Now we predict with all the other models too. And one of them went actually to the GPU and said, please predict, 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 predict with these little mini batches to get the numbers back, right? So we have all this wrapped up for you. You don't need to worry about anything. This just comes back, and it's an H2O frame now. Hence, we can make metrics from this frame, because we have an actual and we have a predicted, and we can compute the metric. And that's actually a new feature we have in H2O. In the past, you would have to ask the model, hey, how are you doing? But now you can actually make a random, like your own column, and then just ask, how is this doing on this actual? So actual is the test set's response. Predicted is this last column. That's the class 1 probability. The last column is this one. Okay? Class 1 probability. That's exactly what test response is. It was 0 or 1, the default next month, right? And let's see if we get this number here. Something like that. So in this case, the deep water is a little worse than last time. This is for the deep learning one. This is for GBM, random forest. And now I'll do a blend of GBM and random forest, and I take like just mean, half-half. That's like Kaggle for beginners, right? You just take two models and you average it. You are not quite a Kaggle master, but you already are doing better than just the GBM alone. So not bad, and much better than random forest alone. So they help each other. And now we add the deep water and deep learning models too. Why not? Oh, even better. It's only the fourth digit that changed, but that's good enough for Kaggle, right? Sometimes it's even the fifth digit. But if you start overfitting now, if you say, okay, if I change this 3 to a 2 and this and that, then it gets ugly, right? You don't want to do this. You don't want to overfit on this 10% split. You want to do this in a cross-validation loop and all that. Be careful not to tune these numbers too much. So now we can go look at this stuff in Flow again. If you go to Flow and you say model, list all models, you'll actually see a bunch of models, right? And you'll see that there's a GBM. The GBM probably has a nice curve of convergence. By default, it scores all the time for the first few seconds, and then it scores every so often to not use too much CPU time to score. But you can specify the scoring interval. You could say I want to score every 13 trees or something, and that makes it more regular. And also that's used for early stopping. So we also stop early if you specify the stopping rounds parameter. So I really highly suggest you look at our documentation because all these methods have cool features like early stopping. You can say once the AUC or the log loss or the RMSE doesn't change by more than 1% over 4 consecutive scoring events, then stop, right? So all these things are built in. You can see the AUC curve on training, on validation, and you can delete the cell with DD. Then you can do the same thing with deep learning. Also nice curves. Let's look at deep water. So deep water with probably the last one. So there's a numbering scheme going on. This was the last model we built in deep water. Okay, converged, but only a 75 training RSC. It's not as good. And as I mentioned earlier, you can inspect this graph. You can ask for each threshold in this area here, what's the F1, F2, and so on. Lots of numbers, confusion matrices, everything. You can also ask, where is my recall the best? Well, obviously, if you specify everything above threshold 0 to be a yes. If you tell everybody should be yes, then you got the best recall because you just remembered everybody who was a 1 is a 1. That's not a good question, but it's still instructive for those who want to learn. You can say, where is your maximum specificity? Well, that's when you say you only get the right ones. Well, that's only if you go to 0.9997, only if you're super certain. Only then you get the right ones and nothing else. And then, of course, there's stuff in between, like accuracy or something. This is the point with the highest accuracy in terms of classification error, and so on. You get gains lift, all kinds of cool stuff. And even the gains lift table itself, you can ask, for example, here, for the first 4% of my data, what is my lift, cumulative lift over this whole 4%, or just in this group from 3 to 4%. All kinds of stuff that maybe people care about that do like, how do I get back? Here we go. Marketing campaigns and stuff like that. So that's that. There is more scripts. For example, we can close and halt this one and go back to the home page of the Jupyter Notebook. We're almost out of time, but I want to show you the Inception ResNet v2 that I mentioned earlier in the other talk. This actually built a model that's super complicated that just came out of Google in August, 300 or 200 layer deep neural net. The definition itself is long. Someone had to code it all up, and we just copy pasted it. It's open source for you. Yep. And then you do the same cat dog mouse, right? You run it, you look at some images, why not? and you run the model. And really all you have to do is you have to export the model as a file, and then you specify it. That's it. And then it runs. But this is the MxNet backend. So if you're not familiar with MxNet, you'd rather have TensorFlow, then you'll wait a month or two and you'll have that too. But in the meantime, you can use MxNet. As you saw, it was actually a little faster than TensorFlow. It's also less memory overhead, so you can fit these big models into a smaller GPU. So if you have a 980 at home with only 6 gigs of RAM, you don't have a Titan X or something with 12 gigs, then maybe you can still fit that model into your GPU if you have MxNet, versus TensorFlow might require more memory. So TensorFlow is kind of the nice framework like Spark, but might not be as efficient at everything as maybe a highly optimized C++ library that does nothing else but just one thing. And one last thing I want to stress is that we also have a fully featured R API. So there's actually a fully featured MxNet R binding package, and these _-r is also grid search. Let's do the iris R. That does an R package, library R, H2O. I'll just run this real quick. It loads an R package. You import an iris data set with flowers. You specify a bunch of grid search parameters, which activation functions, how many hidden layers, what learning rates. You say you want to do a random grid search over all kinds of combinations of these hyperparameters, and you want to do this until you have at least 1,000 models, or you spend half a minute, right? And most likely half a minute will trigger first. This here. And now it's going to be running a grid search from R. But of course, in the end, it's just a string that gets sent to the server, which says, hey, please, MxNet, run this, using our Java logic. But the point is that if you're an R user, you will have full GPU deep learning with Flow and everything. It doesn't have to be just in Python. All right. Thank you very much.
Okay. Thank you, Arno. Do you want to open it for Q&A?
Do we have a question there?
We have one right here.
So the progress bar somehow didn't work here. We have to look at that.
It should be on.
Okay. But you'll see the top models. So the best model was the 2020 model, a small neural net, because it quickly saturated its capacity and learned everything it could. While the other one with 50, 50, 50, 50 maybe needs more epochs to converge. What was your question?
Arno, we had a question right here.
Hi, Arno, right here.
Oh, here you are. Okay.
Yeah, hi. I used to deal with MRI images, so I kind of understand about the convolution and Fourier transform in a spatial sense. In this case, what makes a cat different from a dog? I mean, when you do all that convolutions and Fourier transform and so forth to the image, what are the latent characters that computers actually seeing to pick up a dog being different from a cat?
Well, it's some characteristic that you do too, right? When you see one, you also have to see something that's special about them. And that's it. I mean, there's no difference between you and that convolution that happens here. Your eye does convolutions for you because it's a physical lens, right? And a physical lens does nothing but Fourier transforms. And your brain is then also wired. You have neurons in your head that actually figure out, oh, this is like a cute little kitty nose or something. And that literally triggers neurons in your brain saying, smells like cat to me. And the neural net does the same thing.
So it is really some kind of a facial recognition thing?
Yes, it's
okay.
If you see the face of the cat, then you know. Otherwise, it's the weird shape of the feet or something, or you know what I mean? Or it's a tail or something. There's always some part that you will find. And the model has enough complexity. If it has 1 billion numbers, some of those billion numbers will be used to actually remember the cat's tail, right?
Okay,
but it's brute force. It's brute force memorizing of shapes and features.
Okay, so my question is, I see here that you, after it's trained, you have a JSON file.
Mm-hmm.
Okay, how do I use that JSON file for scoring in production?
The JSON file alone is not enough. You also have when you actually export that model from Steam, for example, you get a zip file that contains the JSON, the graph that we made, but you also have a state of the weights and biases in the neural net, right? And those two together, plus some meta information about what it is, whether it's image or not, and so on, those together will be used to give it to MxNet or TensorFlow at scoring time and say, please instantiate me that model from these bytes, load that state back into the backend, and score it.
Using a Steam.
So we literally store that raw state as a byte array, just like the file itself. The same bytes actually that MxNet would store or that TensorFlow would also store. So we don't do any special formats. We use the native format. So if you have a MxNet state that you download from the MxNet website, that's like the inception model, you can just load that in and you're good to go to score in H2O on a CPU or GPU.
Thank you.
Other questions?
By the way, this image, if you're interested in playing with it, we should be able to provide access to such a public AMI before we make a final release. This is like a pre-release, right? Because it's not finished with TensorFlow and Caffe. But whoever is interested, please let us know. We could make a public version of that AMI. 70 cents an hour. It's not going to hurt anyone. Yeah.
Can you spread the GPUs across nodes? Can you spread the GPUs across nodes, or is it single node?
Currently, it's single node. So the question was, can you do multi-node? So the Caffe implementation I showed earlier has multi-GPU support for one node, but it's not yet multi-nodes. That itself is kind of a research problem, because how do you really take advantage? Do you need model parallelism or data parallelism? And it doesn't really scale beyond 4 nodes unless you have super interconnects. So I would say for the next few months, probably we'll stay with one node, but multi-GPU, which is already pretty powerful, especially if you have these 16 GPU instances.
Okay, we have one question in the back.
So right now, whatever the algorithm does is a specific identification of one particular object within an image. So let's say if I have multiple objects within an image, whether this sort of algorithm will be able to identify the different objects and how it will.
Yes, that's a good question. So currently there's only one label, right? But you could imagine a case where you have 10 labels or 50 labels. And then you have a scene parsing algorithm or something that says this is a human holding a baby cat on top of a yellow whatever chair or something. And that's what Google and others are doing, right? It's not difficult, technically speaking. It's just a bigger neural net that has more inputs and has to be able to deal with multiple things it learns. But yeah, we don't have that right now in H2O because the interface is geared for one response column. It's more like an analytical problem solver than a arbitrary research tool. But you could take this and predict the damage of a hailstorm on a car or something, but take a picture of a car and predicting like the regression output, like is the damage $10,000 or $1,000, that kind of stuff, right? It's regression classification. And soon we'll also have auto-encoding, so you can make features. You can also export, like, let's say, the last layer of this and turn your images into 600 features, for example, without actually letting the model make the prediction, but just make those 600 features. And then you have that 600 column data set instead of a JPEG. And then you could build your GLM on that or something and say, I want a fast scoring model. But of course, you have to transform the data first before you can do the fast scoring. But maybe you can. So there's other options to handle these image problems. But yes, the arbitrary labeling of an image or doing the same thing for a video, for example, or for a sound file, those are all things that are possible. It's just a question of how do we package it, how do we make it accessible. If you want to do top leading edge, bleeding edge research, you just have to use the tools themselves, right? But then you have to compile it and you have to compute the metrics and so on. All right, great. Thank you.
Thank you so much, Arno.